And the title of this talk is called Numeric Programming with Spire. But I have to tell you right from the beginning that the title is actually a lie. Because I'm not going to talk just about Spire. I'm actually going to talk about Cat's kernel, algebra, and Spire. So it's three libraries that work together. And many of the things that I'm going to talk about come from Cat's kernel, some come from algebra, and some others come from Spire. But for the purpose of understanding this talk, it actually doesn't really matter that much. But I will get to that later. So let's just start from the beginning. So what is Spire? I feel like of all the type level libraries, Spire is probably one of the lesser well known. So probably everybody here has heard of cats and shapeless. Spire was there right from the beginning, and it's not as well known as the others, I feel. And if you look at the website, if you look at the README, then you can see that Spire is a numeric library for Scala, which is intended to be generic, fast, and precise. So that's the and. The conjunction is very important. It aims to do all three of these things, because very frequently when you're dealing with numbers on computers, you can be like fast and precise but not generic, or you can be generic and fast but not precise, and also you can be, usually you just have two of them. But Spire actually tries to give you all three of them, and this is really nice. So yeah, it's one of the oldest type-level libraries in that sense, and it was initial work was by Eric and Tom. And I checked yesterday; it has 60 contributors right now. So this is actually quite a large number. And initially, it started out in 2011, but not as a library. It started out as an SIP. So I'm not sure how many people are familiar with that term. So it's a Scala improvement proposal, and it was supposed to go into the standard library at some point. And I actually did some digging, and I found this paper from 2012, which was written by Eric. And it's like an ACM 2-column style, so it's academic, it's legit. So it's an official academic paper. So this means everything I'm talking about now is peer-reviewed and completely fact-checked. And this was held as a talk in 2012 at Scala Days in London. And I think at that time already it evolved from an SIP document to an actual library that was supposed to be freestanding and not necessarily incorporated in the standard library anymore. But so much for a bit of history. So what's in Spire even? And I have put some bullet points in here, and I will elaborate on some of these bullet points, and for the rest of these bullet points, you just have to trust me that they're in there. So there's this thing called algebraic tower, and I will explain that in a moment. Essentially, it's a very big type class hierarchy that fits your every need in numerics. So whatever kind of operations you need on numbers, there's going to be a type class for that. That's in a nutshell. Then, of course, you have number types, because, as you know, Scala has the usual JVM types, float, double, and it also has wrappers around big int and big stuff, whatever big stuff. But some of these types are actually not as useful, and sometimes you need more things or different things, and then Spire's got you covered by providing some extra number types. It also has numeric algorithms. So like algorithms to compute the sine and cosine of these fancy types, and also pretty syntax. So all of these different types, you can just use them as they were regular ints and floats and whatnot. And optimization macros. So this is one thing that I'm not going to go into detail here, but suffice to say, if you feel like you need to write a C-style for loop with a counter, then Spire has macros to allow you to do that and to make it fast. And also, the most important thing, laws. So everything that I mean, as you saw, it's academic, so it's completely legit. So in Spire, there are essentially tools that allow you to check if your algorithms are correct, and also they apply that to Spire itself. So, for example, all of these number types in Spire, they are completely checked that addition and multiplication do what you would expect. And there's also like an entire hierarchy about this, but this is also not, I will mention this, I will demonstrate it briefly in the talk, but I'm not going to go too much into detail there. Right. And now to elaborate a bit on the title. This is the relationship between those different projects, and this has sort of grown organically in the past few years. So initially, there was only Spire. And then there's another library, Algebra, which has been created by the Twitter people. And then at some point, those people got together and thought, well, actually, we have many of the same type classes, we've solved many of the similar problems, why don't we abstract over this? Because we don't want to convert between this type class from Spire and that type class from Algebra. So let's just maybe try to create this library that's called Algebra. And of course, there's also cats. And then it turned out that cats also want some of these similar type classes as Spire and Algebra needed. So then what happened was all of that got pulled out into cat's kernel, which now basically, as the name said, a kernel is smaller than a core in some sense. So you have cat's core here now, which depends on cat's kernel, and Algebra also depends on cat's kernel. So essentially, we're going each of that is a layer that adds more type classes and more types to this. And there's I think there's a very clear delineation of what belongs into what project, but I think that would be a bit too extensive to talk about now in this talk. And then there's also discipline, which is a very small library. It's basically just 200 lines of code, and this is for supporting all of this law checking business. So this is for testing purposes, and it's being used in cats and Spire both. I'm not actually sure if Algebra uses discipline, but Right. And yeah, in this talk, it's basically I'm going to restrict myself to these three things, but you don't actually have to know which of the types and type class I present are in what library, because you can just import 2 or 3 lines, and then you'll get all of the good stuff. Right. So let's start out with this fancy term that's called algebra. And I know that algebra is a term that's being thrown around a lot in the functional programming community, and very often it's quite vague what is actually meant by an algebra. And the good thing is that mathematically speaking, there's quite a strict definition about this. And this definition is here. It's the study of mathematical symbols and the rules for manipulating these symbols. So as you can see from this definition, it doesn't say numbers anywhere. So it's just symbols. These symbols can be arbitrary symbols. Don't have to be numbers. Now, why do mathematicians do that? So why do they talk so abstractly? Well, the cool thing about algebra is that you can essentially abstract over many different things, and mathematicians use that to discover common properties of completely different structures. So you can have 2 or 3 completely different types that do completely different things. But it turns out that they actually have quite similar properties. And this is what you can abstract over with an algebra. For example, you can talk about numbers with addition and multiplication. So that would be one kind of algebra. And you have different number types. You have real numbers, you have natural numbers, you have complex numbers, and all of these support some sort of notion of addition and multiplication. But there's other kinds of algebras. There's also something for matrices and vector spaces. So if anyone here has ever done any kind of programming for physical objects, like some simulations and stuff, you will probably have used vector spaces and like manipulated vectors. And I hear matrices are in again for machine learning. I don't know anything about that, but I hear that linear algebra is a cool thing there again. And then you have this funny business, which is called lattices and Boolean algebra. And essentially, this is sort of like an abstraction over Booleans. So how you discover properties between different propositions. And there are many more applications to that. And for example, if anyone here has a boat license or something, then you have to know about all these knots, right? So there are so many different knots. And there's actually a theory behind this, which is called knot theory. So there are mathematicians who study knots. In particular, they study unknots. So an unknot is a knot that you can just untangle by pulling the strings, right? And it turns out that this is an application of algebra. So you can describe ways how to transform one knot into another by these algebraic theories. So this is actually quite interesting. So this is like some real world thing, and you apply lots of amounts of mathematics on top of it, and then you can do some computations with it. Right, I'm not sure if you have to take math class when you're taking a boat license, but really you should, because knot theory is quite interesting. Also, Rubik's cubes. So these funny things that you can just turn around, which I have never been able to figure out, and you can also describe these movements there with algebra. So you can think of these rotations as some sort of like operations on a group. This is how the structure is called. And then you can sort of like try to figure out how many moves you absolutely have to take, like what's the minimum amount of moves you have to do in order to solve this Rubik's Cube. So what seems initially as some very abstract ivory tower concept that only like the pure mathematicians would care about actually has a lot of real world applications. So that's pretty great. And this is basically all prelude about this, and now I'm going to switch to Scala mode. So now I'm going to show you some Scala code which sort of like concretizes these concepts. And without further ado, here's a semigroup. So a semigroup is a kind of algebra, and if you translate that to Scala, then it's basically just a trait that takes a type parameter. That's literally all you need to do in order to represent such an algebra in Scala. So as you can see here, we have a trait, semigroup, and then we take a type parameter, and that trait has just a single method. And it's a very simple method. It just takes 2 arguments and returns a value, and all of these 3 things are of the same type, right? So the append function takes 2 a's and returns another a. And this is just basically the definition of that semigroup algebra. And I'm not sure why it's called a semigroup. It could have been called an appendable or a concatenable or something like that. It's just what the mathematicians thought about, and this is why we're just now stuck with this. It's just a legacy name. We have to, mathematics is like a legacy system of 2 millennia, and we just have to deal with that. Right, and of course, anybody could implement that semigroup trait and just do whatever, but we want to be law-abiding, so we impose to ourselves that all of these instances satisfy this law, justice, equality. So no matter in what way you parenthesize an append operation, so if you first append y and z and then you append x in front, or if you append x and y first and then append z at the end, then that has to be equal. That's basically the only thing. And essentially, these laws are, like, you know, they're very common for interface. For example, if you look at a Java long object, if you look through the description of equals and hash code, you also have these kinds of laws. I mean, in the Java world, hardly anyone cares about them, but when you're doing this mathematical stuff, you really should be caring about them, because otherwise bad things might happen. Right. But unfortunately, I will speak later about this. But now we can add one more thing to that semigroup, and then we get the monoid. And a monoid is basically just a semigroup, that's something that has an append function, and we just add 0 or neutral element to it. And the neutral element is just, you can consider that to be like a constructor that gives you like an empty thing of some sense. And the additional law is that whenever you take the 0 element and append it to x, then you get the x back. So the 0 element is like a 0, it doesn't do anything when you append it. And actually the interesting thing is that just with these 2 laws, so with this associativity law and the neutral element law, you can prove a lot of other laws. So for example, you can prove that you can also append the 0 here, and then so you can swap these things and it results in the same thing. You can already prove that by knowing nothing else. You don't have to know anything about a concrete structure. And that's really the power of this abstract algebra. You take a small set of laws, a small set of operations, and then you can derive a long list of theorems about, or knowledge about these things. Okay, so this is still very abstract. I've so far only shown you some traits. I haven't shown you any implementation of these traits. And it would be cool if we could just program against traits all the time. We wouldn't have to care about any implementation at all, but it's, you know, at the end of the day, we want to run something. So we need to give an implementation of these traits. And it turns out that many things are monoids. Really, a lot of things. And before I show you some Scala implementations, I want to show you a real-life example. And that real-life example is a train, or rather trains. So I'm going to argue that trains are monoids, right? So if you consider trains, many of them are, well, at least lots of the older trains. So the newer trains are a bit different, but like the older trains in the olden times, they were extremely modular. So you had different kind of carriages. You had a locomotive, for example, that had like active, propels you forward. And then you have carriages where maybe people are in there, or maybe there's cargo in there. And all of these things have couplers. So you have these things in the middle, and these things in the middle help you to connect to carriages, right? And in particular, in cargo trains, you can just connect an arbitrary amount of these things, right? So this is a train, and I'm going to argue now that if you connect these two things together, append train, you get the train again, right? And of course, it's associative, because if you have 3 trains, it doesn't matter if you connect this and this first and then the other one, or if you connect 2 and 3 first and then put it in front of one, right? It's still the same kind of, you still get the same train back. Now, I had long discussions yesterday about what the empty train is, because it requires a 0, right? So what is the 0 for trains? And I'm just going to say, well, no train, right? So if no train has no length, right? It's just not there. And you can append a no train to an existing train, you get the same train back, right? But this is like, we can argue about this anyway. So this is the real life example. And yeah, so you could argue maybe if you don't agree with the notion of no train, then maybe a train is just a semigroup and not a monoid, but whatever. Right. So let's go back to Scala. So the first example you saw is like train, and the empty element is no train, and the operation is couple. But another monoid is integers. And what is of course, when you talk about what is a monoid, we have to give all the methods, we have to implement all of them. So the type is int, the 0 is 0, and the plus is plus. And now we can convince ourselves that this actually satisfies the laws. Well, x plus y plus z, doesn't matter where you draw the parentheses, it's still the same result. And x plus 0 is x, so monoid laws are satisfied. But also list. So when you take a list of arbitrary type, and then you use the append function or the concat function or whatever you want to call it, then also that forms a monoid. Because if you have 3 lists, L1, L2, and L3, it doesn't matter if you append L1 and L2 first, and then L3, or L2 and L3 first, and so on. And also maps. So when you have a map with an arbitrary key type and arbitrary value type, then the empty map is the 0 element, and the merging operation basically means you take 2 maps, take all the keys that they join, or all the keys that they have in common, and then you have to join the values somehow, and the rest you just put them there. And I actually have a quick demo on that, because this map merge operation is not that common. I don't even think there's a function for that in the standard library. But Spire implements it, and it comes in very handy. Okay, so basically what I'm going to do, I'm going to define 2 maps. So I have 2 maps of cities, or countries mapping to lists of cities. So I have for one map that declares that Florence is a city in Italy, and then Lugano is a city in Switzerland. And I've chosen Lugano because it's Italian speaking. And then you have another map which says that Rome is in Italy. Now, you want to merge these 2 maps together and want to get a full map of all the cities you know, and then you want to associate them with all the countries. So in Spire, you can just write this. And you will get this combined map. And it's sort of what you would expect, right? You still have 2 keys, Italy and Switzerland. Both of these keys were present before. But you had Florence from up there and Rome from down there, so these are now together. And I've been told that the data scientists call that map reduce. So you take you have different nodes that produce like a word count or something. I've heard that word count has to be mentioned as an example. So you have like a word count, and then you have to reduce that together, and that's basically just a monoid append operation. And this is actually what makes it lawful, because when you're running a map reduce, you're running the map on different nodes, and you don't know when they will come back or in what order they will come back. So you need to have some mathematical structure that allows you to combine them sort of in an arbitrary fashion. Otherwise, you might end up with some random results by not being able to append that in an arbitrary order. Okay, so that's cool. So a lot of things are monoids, and we can use that in our day-to-day programming. But also, it turns out that there are some types that we would really like to be monoids, but they aren't. For example, floating point numbers are not monoids. And that's really not cool. Because why is float so different from int? Because int 0 plus is a monoid, but float 0 plus is not a monoid. And I'm not sure here how many people have done any kind of high performance computing before, where you have to run stuff on GPUs and stuff. Has anyone done that before? Okay, just one poor soul. The problem is that floating points are actually a lie. So they just pretend to be like real numbers, but CPUs have to do some rounding, right? Because you only have finite space. So it turns out that associativity of floating point numbers is violated. So this law doesn't hold for floating point numbers. So it really does matter how you put the parentheses for floating point numbers, and that's really sad. But this is the way it is. Anyway, Spire still provides the monoid instance for floats, even though it's not lawful. And Eric, the main author of the library, argues that, he can't stop people from doing that. So at least he wants to give them clean needles if they really want to do that. His words, not mine. Okay, but the hierarchy doesn't stop there. We don't just have a semigroup on monoid, because as I said, mathematics is a very old legacy system, so we have a lot of these different things. And this is the basic structure. So you have a semigroup, a monoid, and then a group. And a group is just a monoid, but we also get a subtraction operation. We don't just get an append or an addition, we also get a subtraction. So we can take an element and essentially like inverse it. So for trains, that's going to be complicated because we would need to talk about negative trains that you add and then you get no train. So this is the real world analogies stop there. But for example, if you take numbers again, you can just take the negation of a number, right? So 5 plus minus 5 gives 0 the identity. So we have this as a group. That's cool. But of course, I've talked about the addition of natural numbers. What about the multiplication of natural numbers? And it turns out that the natural numbers also form a monoid with multiplication. It's just that the 0 is actually the 1. Because 5 times 1 is 5. So 1 is the identity for multiplication. So this means that our hierarchy here is sort of a bit restricted, because sometimes you want to distinguish between addition and multiplication. In particular, if you're doing operations with matrices, then it's really important that you have both addition and multiplication. Those are two different operations. And in Scala, you would otherwise get ambiguity errors, right? So you would have a monoid instance for integer for addition and then one for multiplication, but int is the same type, so how you want to distinguish them? So here's what Spire does. It just copies that hierarchy twice. So we have a hierarchy for additive algebras and the hierarchy for multiplicative algebras. And you can see that in the name you have like an additive semigroup and blah, blah, blah. And basically I have put these dashed lines in here because you can convert back and forth, right? So if you're in a situation where you have an additive semigroup and you want just a plain semigroup, then you can convert back and forth, it's possible. But most of the time you would be using this blue or this green one. And of course, it doesn't stop there. Because as I said, sometimes you want addition and multiplication together, and some additional guarantees from that. For example, you want distributivity. If you have a plus b times z, you want that to be the same as a times z plus b times c, right? So you want some additional properties. But this one talks only about addition, this one talks only about multiplication. There's no way to connect these two operations together. Which is why the mathematicians came up with rings. And this has nothing to do with rings to bind them. They're just called rings. I don't know why. Anyway, so rings basically combine the additive side and the multiplicative side, and there are a lot of them. But there are a lot of different flavors of these rings. And don't ask me why, like, there's rig and like rung, I think, and this is ring, and then we have not a ring here, like, but a field. I don't know, like, somehow this makes sense. And the way I do it is I will just open the documentation for Spire and like we'll just figure out like what parts of combination I need here, and then I just pick that and I stop thinking about it. I don't try to make sense of the names, and I'm sure many people have thought very hard about these names, but this is how we're ended up with them. And yeah, for example, if you want to implement an algorithm on matrices, it's very likely that you're actually going to need like a ring, for example, or maybe even a field. And the cool thing is now that all of these things have different laws, and they even inherit these laws in some way. So these laws are defined on these things, semigroup, monoid group, and then they are basically recombined to make new laws for all of these type classes. And the discipline library now allows you to write basically this. So you can say, well, I want to check that, for example, int satisfies the laws of a Euclidean ring. And I feel like I should know what a Euclidean ring is because I'm doing a PhD in formal methods, but I really don't know what a Euclidean ring is above a ring. You have to look at that on Wikipedia, sorry. But I'm going to demonstrate how this law checking works and how essentially when you have your own number type, for example, let's say you're a bank and you have a type for currency, then you want to implement a group for currency because you can add currency and you can subtract currency and you have zero currency. You want to check if all of that works out. I'm not sure about multiplying currency. I don't think that works, but anyway, so you could if you really want to. Right. So basically, you can write this. So you can get this. There's even more support if you're using Scala tests of Specs2, then there's like some trait that you can extend from in your test and then you get more stuff. Essentially this is like raw Scala check here now. And you can see that this runs a lot of tests. So we have hundreds and hundreds of tests. Let me try to make that a bit smaller. Maybe we can see all of the tests that are being run. Yeah, it's a lot of them. And, right. So let's try to run these tests for float. Just to tell you that I wasn't lying, because yeah, for floating points this is actually violated. So many of these properties like distributivity, we have 3 values here which we either add first or multiply first, and it turns out that floating point numbers do not like mathematics, or mathematics doesn't like floating point numbers, whatever. Anyway, so these fail the tests, but you can still use them if you really want to. Yeah. So yeah, I want to switch now to an even more concrete setting. So I told you about all of these algebras and whatnot, but I already also told you that Spire has custom number types, and it turns out that when you're dealing with numbers, most of the time, the default choice, which is int or float, is also the wrong choice. So if you don't take away anything from this talk but one lesson, I want that lesson to be whenever you're dealing with numbers, think for 5 minutes what operations you want to do on these numbers and what precision you need, and then choose a more specific number type, except for int and float. And because the reason why I'd like to stress that so much is because numbers on computers are all about trade-offs. So in mathematics we have real numbers, and real numbers are great because they can basically do anything. You can do all sorts of operations on them, they're closed, you can just take a square root of a real number. Well, okay, let's say complex numbers, because you can't take a square root of a negative number. But you can just do whatever with it. Unfortunately, on our computers, the memory is limited. So we can't just represent pi, like all the digits of pi in our memory. We don't have enough memory for that. So we have to do trade-offs. And floating points are a good trade-off for many purposes. So I know I have insulted floating point numbers in this talk multiple times already, but they're not bad in the sense that they are poorly designed. They are designed for a very particular purpose, and they're designed well for that purpose. I'm just saying that not all purposes are that purpose, right? So they were designed essentially for algorithms where some scientists would think about the error bounds that you require. So floating points have some errors because you have to round, and then they were designed for the use case that someone would look at an algorithm and think, well, I can get away with an error of 10 to the power of minus 9, and then would prove that this works out. But these days, we just use floats and doubles, whatever. It's just like, okay, just a double. We don't care about error bounds. We just like hope that it's all good. And yeah, so there's no one-size-fits-all number type. And we have to think very hard about the use case that we want to do. Maybe we want to deal with currency. And when we're dealing with currency, we really, really do not want any rounding errors if we're like interfacing with some, I don't know, like a client. So you might have a client who expects 10.-8 precision, and you just don't want to say, well, okay, I got a floating point rounding error, tough luck, because that might actually, like, these errors tend to propagate. So, for example, let's stick with the case of currency. A good choice could be to use just rational numbers. And rational numbers are just, just fractions. You have a numerator and a denominator, and they are closed in addition, multiplication. So all of the nice operations that you would use for rings, they are closed for rational numbers. So you don't have to care about any kind of rounding errors. You can multiply them, divide them, and all of that works out very nicely. But of course, trade-offs. So one thing that the problem is with rational numbers, they may grow very large. Because, for example, assume you want to add the following sequence of rational numbers: 1 over 2, 1 over 3, 1 over 5, 1 over 7, and so forth with all the prime numbers. Then these numbers get very large because you cannot simplify the fraction. So you have to, your numerator and denominator may grow a lot. So that may take a lot of memory, but depending on your use case, maybe, for example, you know that you only have 10 numbers to add up, then it's fine, because you then can make an estimate on the memory consumption. Okay, so I want to demonstrate this, and the reason why I picked the rational numbers is because Spire actually provides a lot of nice syntax for rational numbers, and it's just a pity that they're not used more. Okay. So we can write, for example, the following. What did I do? Okay, so you just have to trust me on that. I'm not sure what Ammonite is doing here. There's a... Give me a moment. I think I have even more time than usual anyway, so... right. Sorry about that. Yeah, Ammonite turns out that Ammonite also has an idea of what this R should mean. So let's reset. Right. So in Spire you can use this R string interpolation to actually get nice syntax for rational numbers, and it will also yell at you if you do something wrong. So this will yell at you at compile time, not at runtime. So this is really cool because this is actually implemented as a macro. So the compiler will parse that number and will convert it into something that is fixed. So it's essentially like literals in some sense. And you can also manipulate those things, of course. So let's say I'm writing a function that takes a number and then adds that number to itself. So this also showcases the way that you can deal with these additive monoid type classes and all sorts of other type classes. And then you can call this, for example, on the score. So now you have 10 over 7. And of course, Spire will also simplify these fractions for you. So if you have 2 over 4, then you get the simplified. And just to reiterate on the previous point, this twice function also works with other number types, not just with rational numbers. So it would also work on integers. And of course, if you don't want to print it like this, so this is printed as like an actual fraction, but if you want this to be printed in a decimal way, you can also call it 2-big decimal conversion function. And you get it printed as a, sort of like a floating point number. And the cool thing is that almost all of these number types from Spire have just very simple conversions back and forth. So you don't have to jump through a lot of hoops to convert back and forth. You can just call the appropriate function. I believe there's also like a toInt function probably. Yes, toInt, of course, it's going to be 0 because I chose something that's less than 1. But let's try start toInt. We'll just truncate, but sometimes this is what you want. Okay. So these are rational numbers, but I want to show some more number types that Spire supports. And especially I want to contradict myself now a little bit, because I told you that computers really can't represent real numbers. And that's true to some extent, but we can cheat. We can pretend that we can deal with real numbers. How can we do that? Well, as I said, we can't represent all real numbers on a computer because there are uncountably infinitely many of them, and our computer only has a finite amount of RAM. But we can get arbitrarily close. And so this is a diagram I've listed from Wikipedia, I think. So this is basically a hierarchy of types of numbers that are being studied, that you can study in mathematics. So the innermost thing would be integers, and then you can extend the integers, you get rationals. Then you can extend them to constructible numbers, and constructible numbers are something that you can, like draw on a paper, essentially, with just a ruler and whatever this thing is called to make circles. And then you can extend it even more, and then you have outside you have the reals, and they are completely out of scope. But we can have the subset which are called computable reals. And computable reals sound really like a thing that we could do because it has computable in the name. And you can see already that computable reals, for example, they contain E, and they contain other kinds of constants. So we can actually do a lot of things, and pi is also in there. So we can, for example, do trigonometric stuff with the computable reals. We don't need to do all of that extra stuff, right? So while we can't represent all of the real numbers in our computer, we can represent the cool real numbers in there, and they're like, we don't care about the uncool real numbers, just about these things that we can represent. So how are we going to cheat our way through the real numbers? Well, essentially we say, well, I'm not going to give you the real number. I'm going to give you a procedure, and that procedure says, give me a number of digits that you need, and I'm going to compute these digits on the fly for you. So it's sort of like a future, right, in concrete programming. You don't actually have the value, but you can ask for the value eventually, and you will get the value. And the twist here is that you can give a precision, right? So you can say, I want pi to the precision 3, or I want pi to the precision 30, or I want pi to the precision 300. And depending on how large the precision is, the longer the computation is going to take. And then you can implement all of these functions, all of these methods completely generically. So as you can see, this is a trait. And that trait has no implementation for approximate. But we can implement the plus operator. And how does this work? Well, we have one real number, self, and we have another real number, that. And we want to compute that to a precision that's given here. So we just approximate the first number, and then we approximate the second number, and then we have rational, so fraction, and then we can just add that fraction together. And the reason why there's a +2 here is because we have to account for rounding issues, so we have to increase the precision as we go deeper into the computation. So this is a little bit abstract, so don't be afraid. I will have a demo on this as well. Right, and then we can provide functions that produce a real number. So of course we can just have a function that provides you with a wrapper. So if you already know how to approximate a function, you can turn it into real. And for example, you can also take just an arbitrary rational. And of course, for an arbitrary rational, you don't need to approximate anything. You can just always return that rational number. And now that's the cool thing, because now with just that, we can basically define pi. And pi, according to mathematicians, is defined as that. So we basically take, this is a trigonometric function. So we take the fraction 1/5, and then we compute this function, and then we multiply by 16, and then we subtract something similar, and that's going to be pi. And at no point, so when we write this, so when you write this and run this, at no point will you have pi, but you can ask pi to approximate itself then. Okay? So when you just write this, no computation happens. Nothing happens really, only when you start approximating this. So let's see about that. So you see, nothing, if you just ask for pi, then I will just get, Spire will tell me, well, I don't know, it's not exact, and I don't know, and this is like a closure that is waiting to be evaluated on the JVM. So I can say, for example, pi.double value, and then I get a double approximation. Or if I say, well, the number of digits here really does not cut it. I want to learn pi and memorize it up until 1,000 digits. Then you can do that. If you're the kind of person who wants to memorize pi. I'm not sure, like precision 10 maybe. That wasn't enough. Let's try 20. So this is it. I'm not sure what the precision number actually means. I think it's like bits or something, not digits. So maybe let's try 100. Try 1,000. I think this is probably a problem with printing of too big decimal, but you saw some changes, right? So if we make this a bit smaller. Oh, actually, I could remove this and see that this is a very large fraction, and it's probably not even printed completely because oh no, there's a slash there. There's a slash. There is a slash. And as you see, the larger the precision is, the longer these fractions are going to be. So now it stops being printed completely. So you could, in principle, do that for an arbitrary amount of precision. And as you see, the higher the number is, the longer it takes to compute, right? So the previous things were pretty much instant, but now if I want 10,000 bits of precision, it's going to take a while to compute, right? But this is really cool because it gives you a tool to just reason about real numbers without actually having them. Then only when you need to print them, you can just like ask for a precision of 5 bits, for example. And this is also cool because for floating point numbers, like float and double, you're always fixed to a particular precision. You get like 32 bits or 64 bits of precision. But here you can decide. You can basically say, well, I want just 5 bits of precision because, like, you know, pi is 3, so why not? Okay, so the final thing I would like to present from Spire is interval arithmetic. And why would I care about intervals? Well, very frequently, you need to reason about error bounds. And for example, you say, let's say you're writing some software that reads some sensor data, like temperature diagrams or precipitation or anything like that. Whenever you read something from the physical analog world, you will have error bounds. Because the real world doesn't care about our bits. It's just like some value in some frequency range. And these inputs are not accurate, so we want to track how good we know, how well we know these inputs. So maybe they're accurate up until half a second, or maybe just 1 second. So we need to store that sometimes. And Spire offers us a feature, or gives us capability to reason about this. So there's a type that's just called interval. And it's a very simple case class, right? So you just have a lower bound and an upper bound. And this is basically all there is. It's just a tuple of 2 numbers. And then you can just define an addition operation. So you can say, well, if I want to add 2 intervals together, then I just take the lower bounds and add them, and take the upper bounds and add them. Of course, in actual Spire implementation, it's a bit more complicated because you may have open or closed intervals. For example, when you say in the range of 5 to 10, do you include 10 or not? Like, is 10 in the range or is it not? Same for 5. It could be like just in between 5 and 10, or it could be from 5 to 10. So you can do the distinction, is it open or closed, and also it can be bounded or unbounded. So for example, you could have an interval that says 5 up until infinity. And then you can just deal with that. Spire gives you all the tools to deal with that. So for example, when you want to talk about confidence intervals, let's take back our score. That's 5 out of 7. And then, for example, we want to talk about a confidence interval. And now here's the cool thing, because Spire also has Unicode syntax, so you can write plus minus. If you don't like the plus minus operator, you can also write just plus minus, I think. Or not, maybe not. But just use plus minus, right? So just get yourself a proper keyboard to type this. And then you can't just, so you can of course do arithmetic operations on this, but you can also do stuff like you can talk about intersection of these intervals. So for example, you can ask, well, this interval, does it intersect with this other interval? And that, yeah, it does. or you can actually compute the intersection. So you can, for example, ask, give me the intersection of these two intervals, and it will do that for you. And it will deal with bounded and unbounded and open and closed automatically for you. You don't have to do anything with that. And I think this is really a great tool. It's just that there are not that many use cases for it, but still sometimes it is actually quite useful. Right, so just to wrap this up, Spire is full of tools you didn't know you needed. And I hope that I could give you a nice tour through all of these things. Of course, my tour was just the tip of the iceberg. There's a lot more where all of that came from. For example, there's savelong, and savelong is like big int but faster. And the reason is because savelong internally is a long, but if it's too large for a long, it switches to big int. So most of the time you can just deal with a long, and it will detect overflow for you, and if it's overflowing, it will switch back to big int. Right? So this is really cool. When you're home from the conference, go through your code base and replace all longs with savelong. Thank me later. So there's trillion. So whenever you want true, false, or null, you can also use trillion to make it a bit safer. Well, what else? We have unsigned numbers there. So if you want positive integers, they're present and they're fast. We have natural numbers because when you're talking about, for example, database IDs, you do not want longs because they can't be negative. You use natural numbers. They are always positive. You can't get an ID of -1 because that would be bad. And finally, appreciate your maintainers. These are the 4 maintainers of Spire, and there are 54 other contributors, and they have done a lot of work in order to make Spire fast and generic and precise. So next time you're using Spire, just tweet at them saying, like, thank you for making my numeric code much better. Yeah, so this is kind of ties into Heather's point. If you find a bug also, you can also not just say thanks, but say, file a PR to get it fixed. Spire these days is not a very active project, as you can see, so there was a lot of activity like 2012 to, I don't know, like 2017 with a small break in here. But the reason is that it's really a mature library. It's not that it has stagnated because nobody cares about it anymore. It's just that it has a lot of tools that are stable and that are mature. So it's not actually, you don't actually need a lot of refactorings or a lot of code additions to make this work, because many people found that they're perfectly happy with what's in there. Of course, still, if you find a bug, there might be bugs, then please feel free to send a pull request. And with that, thanks. Open to questions. Yeah, also thanks a lot to Ifan, who has kindly spiced up my slides with these drawings of trains. It was really great.
Any question? It's a lot of happy users. That's it. It's a mature project, no questions. Okay, if there are no questions, we can take a short break, 20 minutes break in the coffee area, and we'll meet back here in 20 minutes. See you later. Thank you, Lars.